So hello everyone, I'm Hanze Zhang from Shanghai General University, iPads Lab, and today I'm going to share my work around the fast and scalable distributed log manager. Distributed systems are complicated, but I'll make this talk simple. So in distributed applications like databases and file systems, workers on different machines might access the same piece of data simultaneously. To serialize these conflicting accesses, distributed logging is necessary. In the typical use case of distributed logs, application workers are required to acquire the log before accessing the corresponding data, and release the log after accessing the corresponding data. While the release operation can be asynchronous, the acquire operation is on the critical path of data access and has direct influence on the application performance. Recently, we observed two trends in the evolution of distributed in-memory applications, which introduces new requirements to distributed log services. Firstly, the execution time is decreasing to microsecond scale, which renders the latency of log acquisition significant in the end-to-end latency of distributed applications. Secondly, the scale of shared data is growing to near billion level, which require a large number of logs for protection of this data. To conclude, modern distributed logs should be fast on acquisition and scalable on the number of logs. Before diving into specific log service designs, let me briefly introduce the typical architecture of log services. Applications acquire and release logs through the log client, LC here, which translates these operations into network requests toward the log manager. The log manager is responsible for deciding whether the log can be granted to the requester according to the log mode, which can be free or shared or exclusive, etc. It also records the requester as a holder if the log can be granted to the requester, and as a waiter if it cannot. This metadata are maintained in a log table. The log manager will reply to the log client when the log is granted to the requester, which the log client awaits on acquisition. Therefore, from this process, we can see to build a fast and scalable log service, the log manager should be efficient enough on log request processing and maintain a sufficiently large log table. Unfortunately, existing log manager designs fail to achieve these goals. The conventional log manager design is placing all of the logs on dedicated servers, so we call this approach server log. While being scalable on the log number because servers have sufficiently large DRAM, server log is slow because it relies on server CPU for processing log requests, which is not fast enough. So the request will queue up in the request buffer on the heavy loads and causing high queuing delay. According to our micro benchmark, due to this queuing delay, server log exhibits more than 1 order of magnitude latency variance on the various read-write ratios and various of skewnesses. Recently, programmable switches have been exploited to host a fast path log manager called netlog. Due to the strong packet processing power of switches, netlog can achieve near zero queuing delay, so it processes packets really fast. But netlog is non-unscalable on the number of logs because programmable switches typically have very limited on-chip memory capacity, so it cannot store enough sufficiently large log number and their metadata. So due to this poor scalability, netlog achieves very limited acceleration when managing a large number of logs. In our micro benchmark with 1 million logs, netlog can only manage less than 1% of logs on the switch, and therefore it accelerates only 1% of requests in uniform workloads. Even if the workload is highly skewed, for example, following the fan distribution, netlog at most accelerates 30%. Moreover, the fast-path solution is highly workload sensitive because it requires static profiling to determine which part of logs should be managed on the switch. If the hotspot or workload dynamically changes, even if netlog can accelerate log granting at the beginning, it will quickly fall back to server log after the hotspot changes. To address the performance issues mentioned above, we revisited the log acquisition process to seek a new log manager design. Our key insight is that the log acquisition process can actually be decoupled into two phases, called grant decision and metadata maintenance. Specifically, the decision of whether the log can be granted can be made solely relying on the small and fixed-size log mode, leaving the large and variable size metadata to be updated later in the maintenance phase. And more importantly, after we make the decision, the grant reply can be sent immediately, leaving the maintenance to be done asynchronously. Based on this insight, we propose a new principle of designing log managers called log fission. Following this principle, we decouple the log manager to switches and servers to embrace the best of both sides. Specifically, the decision phase is executed on switches for fast execution and saving the switch memory, while the maintenance phase is executed on servers for large metadata storage. Since the switch is in the center of a rack, the decider is designed in a centralized and stationary manner, recording the mode of all logs in the rack. The rest of log metadata are maintained in per-log agents on servers, which are dynamically migrated among servers for load balance. Based on this log fission principle, we propose a fast and scalable distributed log service called Fission. Fission implements the decision phase on programmable switches as a request processing pipeline, and it maintains an agent pool on each of the servers for managing the agents of the log it is holding. Fission is very fast because it fully exploits the packet processing strength of switches for critical path decision, and it is scalable on the number of logs because it stores the majority of metadata on servers instead of the switch. To help you understand how Fission works, I'm going to present a few examples of log operation workflows. So suppose that client A is going to acquire the log. It will send an acquire packet to the decider. If the log is free, the decider will grant the log along with the agent to client A on server 1. So the agent will be then managed by the server 1. But if the log has been held by another client, for example, client B on server 2, the decider will forward the request to be processed by the agent on server 2. And the agent will add client A to waiters. And if the log can be shared by client A and client B, the decider will forward the request and grant the log simultaneously for fast path granting. So in this case, the maintenance of the metadata is done asynchronously on server 2. When releasing the log, if the agent does not exist locally, the client must send a release packet to the decider, which forwards the packet to the correct position of the agent, which is server 2. And then server 2 would remove client A from the holders. But if the agent is local, the release process can be done locally. And if there are waiters after all of the log holders have released the log, the first waiter would become the new holder. And then server 2 here will migrate the agent to the new holder server. In this case, it is server 1. So it sends the agent with the grant reply to server 1. And when the grant reply passes by the decider will update the mode and agent location according to the grant packet, and then forward the grant packet to server 1. So this way, the agent is migrated to server 1 on demand. So while the log fission idea seems simple, realizing this principle is very challenging because now the log operations are actually distributed. In conventional designs, log operations are executed by a centralized log manager, but now they are cooperatively executed by the switch and the servers. So this raises concerns like how to ensure the consistency between the log metadata in the decider and those in agents, and how to handle those network exceptions, including lost, reordered, and delayed packets, which are really annoying. For example, if the acquired packet is lost between the decider and the agent, the log mode has been updated, but the rest of metadata in the agent remains unchanged. How to prevent this? And how to tolerate failures. For example, the switch will fail and the server will fail independently, or they will fail simultaneously. How to recover from failures of this with minimal overhead. So to address these challenges, we designed a new log fission protocol and prove its correctness. For simplicity, we will not dive into the protocol details in this talk. Please refer to section 4 in our paper if you are interested. Another challenge comes from efficiently utilizing the switch memory with rather restricted layouts. Firstly, switch memory is organized as fixed-size registers, which are at most 1 byte large. But the log mode is actually only consumes 2 bits. So this unit is too large for log mode, causing memory waste. An intuitive idea is packing multiple log modes in 1 register, but that is not applicable on the programmable switch because each pipeline stage allows accessing exactly 1 register. So we cannot access partial or multiple registers and cannot do packing. And moreover, there is no shared memory across pipeline stages, which means those memory used by control stages are simply wasted. To conquer these restrictions, we carefully design each stage in the decider pipeline to maximize the utilization of the switch memory. Our design manages to support over 1 million locks, which is 2 orders of magnitude higher than the state-of-the-art NetLock. Again, for simplicity, we omit the pipeline design details here, so please check the paper out if you're interested. So we evaluate FISLock against existing lock manager designs using the cluster with 8 logical nodes connected with an Intel 2-FINO switch. All systems use 80 cores for clients and 8 cores for lock managers or agents. Firstly, we use a micro benchmark containing different read-write ratios, including write-heavy, read-mostly, and read-only, and different skillnesses, including uniform and defiant, to evaluate the performance of FISLock against our baselines. As shown in the figure, FISLock achieves low and stable lock-grant latency under all kinds of workloads, while servlock and netlock exhibit apparent queuing delay. So we conclude that FISLock has low and stable grant latency on the various workloads. And we use the same micro benchmark to evaluate the scalability of the lock number. In this benchmark, different number of locks are used to protect 10 million objects. At the beginning, when the number of locks is small, the throughput of both netlock and FISLock are fairly low because of high lock contention. But as the number of managed lock increases, the lock throughput of netlock would quickly collapse after the lock number exceeds its switch capacity, because then most lock requests will be served by the slow path server instead of the switch. However, the throughput of FISLock keeps rising because it has orders of magnitude higher switch capacity. Consequently, FISLock achieves 2 times higher peak throughput than netlock. When managing 1 million locks, it outperforms netlock on throughput for over 5 times. So we conclude that FISLock can manage millions of locks efficiently. We additionally use a dynamic workload to evaluate the workload sensitivity of FISLock. As shown in the figure, the throughput of FISLock remains high regardless of workload changes, while netlock falls back to servlock after the hotspot changes. So FISLock achieves stable performance regardless of workload patterns. Finally, we use a transaction benchmark to demonstrate the end-to-end performance of FISLock in distributed applications. It shows that FISLock can accelerate the transaction processing into representative benchmarks, including TATP and TPCC, for around 2 times as compared with existing lock manager designs. Okay, so to conclude, distributed lock services need to be fast and scalable. To achieve these goals, we propose a key technique called lock fission, which actually decouples the lock acquisition process into grant decision and data maintenance phases. During this, realizing the lock fission idea, we met challenges about distributed lock operations and how to design the on-switch decider in a memory-efficient manner. The details of this part can be found in the paper. And in our evaluation, we show that FISLock can cut the tail latency of lock granting of lock managers by over 90%, and boost the transaction throughput for 2 times. Moreover, FISLock can scale to millions of locks efficiently, which is more than 2 orders of magnitude higher than existing lock managers. Thank you, and questions?